Hello, ladies and gentlemen. Today we are going to be talking about Unit 7, Lesson 2, finding the perimeters and area in the coordinate plane. So today what we're going to be doing is we're going to be taking what we've learned about areas and perimeters in previous classes, and we're going to be just sticking that onto the two-dimensional coordinate plane, onto a graph, so that we can just, find the areas of shapes given a different format. So let's get right into it. Now, for this stuff, I really think that honestly, the perimeter is going to be the harder of the two things to find as opposed to the area. You'll notice when we do these notes, a lot of times we're going to be spending the bulk of our work actually trying to find the perimeter as opposed to finding the area. But let's get into it. The first thing we got to do is we got to plot these points. Okay, so remember the first number corresponds to the x, the second number corresponds to the y. Let's plot these points and get this taken care of. So count over 1, 2, 3, 4, 5, 6, 7, 8, and up 4. 1, 2, 3, 4. Plot that first point right there. 8, -1. Plot that point right there. And then -4, -1. 1, 2, 3, 4. Down 1 right there. Cool. So we will have this kind of triangle shape right here. Ooh, that's not a pretty triangle, but all right. So we got a triangle shape there. To find the perimeter in the figure, we got to find what all the different sides added up are going to be equal to. So for two of these sides, pretty easy. All we got to do is count them. So 1, 2, 3, 4, 5. So that's got a length of 5. And then here, this has got a length of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So we got 5 and 12, but we need to find this missing side. So if you know your Pythagorean triples, you could figure that out really easily. But let's assume we don't and try to figure that out. And the way we're going to do that is with the Pythagorean theorem. So with these two sides being our, our legs of our triangle, and this side being our hypotenuse, we're going to let that be C. And we are going to solve this for C. So when we do this out, 5 squared is 25, 12 squared is 144. Add those together, we get 169. That's going to be C squared. And then to get C by itself, we have to square root both sides. So when we square root both sides, we get 13 is equal to C. So that's what our last side there is. It's 13. But again, it asks for the perimeter. And to find the perimeter, we need to add all the different sides up. So here, the perimeter is equal to 5 plus 12 plus 13. Which is going to be equal to, what is that, 20. So your perimeter for that first one is 20. Now, for the area of the figure, what we're going to have to be doing is relying on the area formulas that we've been learning the past few classes. So for this first one, we have a triangle, and it's a right triangle. So the area of a right triangle is going to be equal to 1/2 the base times the height. Okay. In this case, our base and our height are going to be 5 and 12. So we just take those and we plug them in for the base and the height. Since it's a right triangle, it doesn't matter which one we plug it in for. So 5 and 12. And when we do that, we are going to end up with 30. So the area is 30. Cool. So that's the case for a triangle. Let's move on to some different figures and some different problems here. So now we are going to be plotting a square with the coordinates of that. And we are going to dilate the square using the origin as a center and a scale factor of 4. All right, so the first thing we got to do is plot all these points of our original square. So we're going to start it off doing that. 2, 2, 2, -2, -2, -2, and -2, +2. So there we go. We got this square here. Part A asks us to find the area of the first square. So finding the area of a square is just one of the side lengths squared. And we know the sides here have a length of 4. So the area is just 4 squared, which is 16. Now they want us to dilate the square using the origin and the center and a scale factor of 4. Okay, so what that means, if you think back to our original, one of our first units of transformations, dilating it means that we are going to be multiplying each of our original points here by 4. So both the x and the y are being multiplied by 4. So to do that, 2, 2 is going to turn into 8, 8. So let's plot that. 1, 2, 3, 4, 5, 6, 7, 8, and all the way up here to 8. Okay, you're going to do that to each of the points. You're going to multiply the x and the y by 4 to get this much, much larger square here. Sorry, these aren't super straight. I'm doing this with a mouse, so you're going to see some ugly handwriting today. All right, so we're going to find the area of the dilated square. So looking here, if I were to count all these out, I'm thinking it would be 16. So the area of this shape is going to be 16 squared, which is going to be 256. All right. Part C says to divide your answer to B, so 256, by your answer to A, which is 16. And we are going to compare this to the scale factor. So if I were to divide 256 by 16, you are going to end up with 16 as your answer. So my question to you guys is, what is the relationship between 16 and 4? What do you guys notice about these two? What's the relationship between these two numbers? Well, if you've guessed that 4 squared is going to give you 16, you'd be right. So if you have two figures that are similar, the ratio of the areas equals the square, or the scale factor, squared. Nice. So that's a little note. I don't know how many problems, I'm not sure how many problems we have like this, but this is just a good thing to keep in mind when we start dilating stuff and doing stuff like that. But let's move on. So that's some square stuff. Let's move on. We got, looks like we have 3 points here. So it looks like it's going to be another triangle problem. So let's plot these points. -4, 0, 1, 2, 3, 4. Well, my first point there, 0, 4, 1, 2, 1, 2, 3, 4. Put that point there, and 4, 0, 1, 2, 3, 4. Okay. Yeah. So looks like we got a triangle right here. All right, so we gotta find the perimeter. Now, unfortunately here, we don't know any of the missing or any of these sides except for this bottom side. I think we know that. It's 1, 2, 3, 4, 1, 2, 3, 4. So the bottom side has a length of 8. But these two other sides, we don't know what they are. So what we're going to do in order to find those is we're going to draw a height. We're going to need this height anyways to help us find the area. And what that does is that kind of splits it splits this thing into this bottom side into two congruent parts, which is kind of nice. And it allows us to find this missing side. What's the length of this height? We can actually just count that out. 1, 2, 3, 4. It's got a length of 4. So now this shape here, this right triangle I have here is actually a special right triangle. It is a 45, 45, 90 triangle. Okay, so when we have a 45 or an isosceles right triangle, which is a 45, 45, 90 triangle. And remember, when we have a 45, 45, 90 triangle, it always follows this pattern over here. So we can easily find the last side because the last side is just, root 2 times the other side. So it is just going to be 4 root 2. And then same thing on this left side, it's the same exact triangle. So this side is also 4 root 2. So in the end, the perimeter is just all the sides added up. One of your sides is 8, and then your other side is 4 root 2. Now, you can leave this answer as is right here. This is in simplest radical form. If we are asking for a estimated answer, you would just plug this into your calculator and get an actual decimal number. But you can leave it like this. For me, ask your math teacher what they want you to do. All right, so that's perimeter. Now that was the hard part. Now all we got to do to find the area is just plug in the stuff we know into our formula. So for a triangle, remember the formula is 1/2 base times height. In this case, the base that we're going to be using is this bottom side here, which is 8. And the height that's going to be perpendicular to that, we already know the length of that. That is going to be 4. So then 1/2 8 times 4 is just going to be 16. So the area is going to be 16. 4 times there. All right, cool. So that's one example. So a key thing to take away from this problem number 3 is that you need to be strategic about where you draw your height, because that can help you easily find the other legs. Let's try this one. This one's not so nice. So I'm going to use a different color. Let's use this color. All right. So let's plot these 3 points. -2, 0 is going to be right here. 6, 6. 1, 2, 3, 4, 5, 6. And up 6. 2, 3, 4, 5, 6. It's going to be right there. And then 0, 0 is going to be right here. All right. Ooh, this is looking like a weird little triangle. So I'm going to connect these dots. Oh, you're going to have to excuse my awful drawing here. All right. Ooh. All right. I'm going to redo that last one. That was the worst of all 3 of those. All right. So here we got a weird looking triangle. Okay. It's got 3 sides. I'm sorry they're not straight. Again, I'm doing this with a mouse, so cut me some slack. But here you go. So we got our triangle. We need to find the perimeter. Unfortunately, we only know this one side down here. So these other 2 sides are unknown to us, and we can't just count them. So what we need to do is we need to do what we did before and draw a strategic height. Now, remember, the height's got to be perpendicular to the base, and the only base we know is this 2. So what I'm going to do is I'm going to draw a height here that's going to be perpendicular to kind of the horizontal line that this 2 is on. So if I were to extend this line out here, the height I drew is going to be perpendicular to this base. So we can just count this out because it's on those nice lines. So the height of this is going to be 1, 2, 3, 4, 5, 6. It's going to be 6. And then this is going to be 1, 2, 3, 4, 5, 6. 6 down here. All right, that's great for us because this pattern, this triangle here, should look familiar, like we just did it in the last problem. It's a isosceles right triangle, which means it is a 45, 45, 90 triangle like we had up here. So we can easily find the hypotenuse. It is just going to be 6 root 2, just like we did up here. We just took the side length and we multiplied it by root 2. All right, so that's one of our sides. Now the other side here, this last side, I'm going to call this last side X. This last side X is going to be a little bit more difficult to find because we need to do a little like more work. What we really need to look at is this triangle. It's not going to let me do that. What we really need to look at is like this big triangle here. We need to look at this big triangle here in order to find that last side of X. Okay, so to do that, we got to use the Pythagorean Theorem. We'll stick with yellow. Let's see how that looks. We know one of our sides length is 6. Ooh, I'm not using that. Does not look good. Use this color. We know one of our side lengths is 6. So we're going to do 6 squared plus the other side length, which this total side length here is going to be 8. And that's going to be equal to our last side length there, which is X. So add these up. We square these, 36, 64. 36 plus 64 will give me 100. And then you square both sides and you get 10 is equal to X. So this last side has a length of 10. All right. Now to find the area based off of that, like I said, the area is going to be a lot. Oh, we're not done. Actually, we got to find the perimeter. Found all the side lengths. Now we got to find the perimeter. So the perimeter, again, is just all the sides added up. So now that we know all the sides, we just got to combine them. So the perimeter is going to be 10 plus that last bottom side, which is 2, plus the side we found earlier right here, which is 6 root 2. So combine like terms. The only things we can really combine here are this 10 and this 2. So when we combine them, we're going to get 12. So we're going to get 12 plus 6 root 2 as the perimeter. And again, plug it into your calculator if you want an exact value. Okay. Now let's find the area. So again, like I said, the area on these guys are really easy compared to the perimeters. We've already done all the work for the perimeter, and now we just need to plug it into the formula. So the base we started off with was this bottom side 2. So your base is 2, and the height that is perpendicular to that base is going to be this side here, which is 6. So 1/2, 2 times 6, which when you multiply that out, will just give you 6. All right. So that's the case when you have like a really oblong like triangle thing. So again, the big takeaway is be strategic about where you draw your height. You always want your height perpendicular to the base. And it's really nice for these problems if you can make it vertical or horizontal, because then you can just count out how many spots it is. So keep that in mind as we work through. All right. And we got only one more lesson or one more example to do, and then we're gonna do this area of a trapezoid down here. But let's get back to this example 5. Let's start off the same way as all the other ones and plot the points. So we're gonna plot 6, 6. 1, 2, 3, 4, 5, 6. Up 6. 1, 2, 3, 4, 5, 6. Okay. 4, 4. 1, 2, 3, 4, 3, 4. Good. -2, 4. -1, 2, 1, 2, 3, 4. And 0, 6. So 0, 6. All right. let's connect the dots here best I can. All right, so as we're filling in these last lines here, this should look like a kind of a familiar shape. It looks like bacon. No, this is actually a parallelogram. It looks like a parallelogram at least. But how can we verify that's a parallelogram? Well, the definition of a parallelogram is that the opposite sides are parallel. So these opposite sides here, they are parallel. They're you know, they have the same slope of 0. They're not sloping up or down at all. And then these last sides also are going to be parallel, okay, because the slope of both of these sides is just 1, right? We would count up 1, over 1, up 1, over 1 to get to the other dot. Same thing down here. Start at 1 dot, go up 1, over 1, up 1, over 1. We would find that both of these lines here have a slope of 1. So they are, since they have the same slope, they are parallel. Okay. Not that bad. So now we're just going to do the hard part of finding the perimeter. Now we know already just these top and bottom sides here are easy to find. You just count them out. So the top and bottom sides have a length of 1, 2, 3, 4, 5, 6 up top and 6 down below. And then the sides have a length of, oh crap, we can't really count those, can we? So what we need to do is we need to be strategic just like above, and we need to draw some good heights. So what I'm going to do here is I'm going to draw a height here, and I'm going to draw a height here. And what that does is that creates a nice triangle for us again. This height has a length of 2, same thing over here, and this has a length of 2 on the sides here. If I were to just count from this point over, and from this point over, that would have a length of 2. So again, what we have here is an isosceles right triangle. So we can use our pattern up here that we've had before, this x root 2 pattern again, to find the length of this last side. So this last side is just going to be 2 root 2. Same thing over here. Nice. Now that we have that, we can actually write out the perimeter. So the perimeter is going to be equal to 6 plus 6 plus 2 root 2 plus 2 root 2. 2 root 2. Let's combine like terms. When we do that, we're going to have 12 plus 4 root 2. And that is our perimeter. All right. Like I said, perimeter is easy. Now just doing the area. The area formula for a parallelogram is just base times height. And we know all the bases. We know one of the heights. So all we got to do is plug those in. The height we found is 2. And the height so the height we found is 2. The height here corresponds to this base or these bases. So it is going to just be 6 times 2, which is going to give me 12. That's our area. Okay. Lastly, so that's all the coordinate geometry in a nutshell. So my key tips, the key things to take away, I'm going to write right here. Be strategic about drawing the heights. If you have a nice height drawn, like we had in this problem up here, or any of the problems above, it makes the problem so much easier to do. So be very strategic about drawing the heights. That's my big takeaway from this. Okay. Lastly, so we're just going to talk about this real quick. The area of a trapezoid is this, so it's just another formula you guys got to know. So the formula is just the area is equal to 1/2 the height times the sum of the bases. And remember, trapezoid is a figure with two parallel sides, and the other ones aren't parallel. So all we have to do is we have to take the corresponding parts and plug them into the spots they go. So this 7 here is one of my bases. This 13 here is my other base. So I'm going to take both of those, plug them in for the bases right there. And then the 5 here is my height, and that is going to go in the height spot. So the area in the end is just going to be 1/2 of 5 times 13. Oh, whoops, I guess I should do it. Doesn't matter what way you do it, but just add those two together. And you get 20 times 4. So I think you get 50 if you plug all that into your calculator. And that we're not going to place a huge emphasis on this, but we wanted to show it to you guys, make sure you guys have the actual stuff. But yeah, that is Unit 7, Lesson 2, Coordinate Geometry. Find the perimeters and areas in the coordinate plane. It's, again, I want to reiterate, it's exactly like what we've done before with area and perimeter, but now we're just putting it on a graph. All right, so the same rules apply. You know, use the Pythagorean Theorem. You have to draw good altitudes, but now it's just on a graph. That's the only difference. So thank you guys so much for listening, and good luck with your class. Bye.